Okay, so let's start. Today we'll solve Gate Gate 2022 questions. We'll solve two questions from real analysis. Question number 18 and question number 38. So let's first start from question number 18. Let me play the video. Okay, so today we'll solve Gate 2022 questions from mathematics. This is a question from real analysis. It's a question number 18. It's saying that the real sequence, iterative sequence is given. Xn is xn minus 2 by 2, xn equals to xn minus 1 by 2 plus 1 by xn minus 1 for n greater than equals to 1. Then 4 options are given. You have to check which one is correct. Yeah, so we will do this, and for this is the NPTEL reference. Okay, so let's start. So you have to check basically when this sequence converge or diverge. So xn is given by xn minus 1 by 2 plus 1 by xn minus 1 for all n greater than equals to 1. So in order to check that this is defined by recursion, right? So we'll check that this is, if you start with some initial condition, we'll show that this is either monoton increasing or decreasing or bounded above by below. Right, so let's check first. So for that we need to check that xn minus 1. So basically put the values. So this will be xn minus 1 by 2 plus 1 by xn minus 1 minus xn minus 1. So then it will become 1 by xn minus 1 minus xn minus 1 by 2. Okay, so therefore if you simplify this, then we will get 2 minus xn minus 1 square. Right, so you have to check when this is either greater than or less than 0, right, in order to check that this is monoton increasing or decreasing. So let's first start. So two cases are needed here. Note that x, so for n equals to 0 x naught, so x naught should be non-zero, otherwise this will not be well defined. So let's first take the initial condition, this x naught is positive. Case 1, x naught is positive, then what will happen? So if x naught is positive, then note that by this, how the sequence is defined, all xn's are positive. So xn is become a positive sequence. Xn become greater than 0 for all n belongs to natural number. So we get that this is a positive sequence, and now I have to check that this numerator, what will happen to this numerator. So basically we have to check this. If you check xn minus 1 minus 2, let's check what will happen to this. So what is xn minus 1 minus 2? So this is by definition xn minus 2 by 2 plus 1 by xn minus 2 minus 2. If you simplify this, so what will happen? 2xn minus 2, xn minus 2 square plus 2 minus 2 into, so let's check this one. It will become 2 root 2 into xn minus 2. So the numerator become xn minus 2 minus root 2 whole square by 2 into xn minus 2. Now note that we have chosen the x0 to be positive so that all xn's are positive. So this quantity is always bigger than 0, right, or equals to 0. So which implies that xn minus 1 is bigger than root 2 for all n greater than 2, right. So basically xn, so which is same as xn is bigger than root 2 for all n greater than 1. So this is saying that xn, the sequence xn is bounded below. And now what? So we have seen that xn minus 1 is greater than root 2. So xn minus 1, which is, if you take the square both sides, so what you will get, xn minus 1 square is bigger than 2, which is same as 2 minus xn minus square is less than equals to 0. So the numerator is less than 0 means, so from here we can say that this, because we have chosen x0 to be positive means, and the numerator is negative and the denominator is positive, so overall this will become negative. So therefore xn minus 1, which is 2 minus xn minus 1 is square by 2xn minus 1, which is less than equals to 0, right, because xn's are positive sequence and 2 minus xn square is less than 0, so which implies this xn is less than xn minus 1 for all n greater than 1 or 2. Whatever, it's fine because we need after sometimes. So xn is monotonically decreasing sequence, monotonically decreasing. So what we will get, xn is bounded below and it's monotonically decreasing, so it will converge. So therefore xn will converge to some point. L, let's say, means the limit n tends to infinity, xn is L. So if limit n tends to infinity, xn becomes L. So now take the limit in the initial recursion as we have xn equals to xn minus 1 by 2 plus 1 by xn minus 1. So taking limit as n tends to infinity, taking limit as n tends to infinity, the left hand side become L, right hand side also become L by 2 plus 1 by L. So if you simplify this, what you will get, L by 2 equals to 1 by L, means L square is basically 2 or L is root 2. So the sequence will converge to root 2. So therefore limit n tends to infinity, xn is root 2. So we have, this is the first case that where x0 is positive, so then we have shown that the sequence will converge to root 2. Now case 2, let's take. So when x0 is negative, then what will happen? So again, so this time what will happen if x naught is negative? So now check this one, xn minus 1 plus root 2. Let's check. No, first note that if x naught is positive negative, then xn, which is by the definition, is less than 0 for all n belongs to natural number. So this is a negative sequence. Okay, so now check. Let's, so again this will, so we have to check that xn minus 1 plus root 2, xn minus 1 plus root 2. So let's write down the definition. What is xn? So xn minus 2 by 2 plus 1 by xn minus 2 plus root 2. Now simplify this one. What we will get? Xn minus 2, xn minus 2 square plus 2 plus 2 root 2 xn minus 2. Now what will what is the numerator? Numerator is xn minus 2 plus root 2 square by 2 into xn minus 2. So note that we have assumed that this one is, so this is x naught is, because xn is a negative sequence, so this will become always less than equals to 0. So what does this mean? This means that, so xn minus 1 is less than equals to minus root 2 for all n greater than equals to 2, which is same as saying that xn is less than minus root 2 for all n greater than equals to 1. So this is saying that xn is bounded above, so which implies xn is bounded above, xn is bounded above, bounded above. So now we have to check, so that we have get xn is bounded above. Now you have to check if xn is monotony increasing or not, so then it will converge. So what we have? xn minus 1 from earlier, so this one we have got, right? So now note that this, so xn is, so now note xn minus 1, so this is less than minus root 2. So and also that xn minus 1 is a negative sequence, so multiply both side by xn minus 1, so we get xn minus 1 square is, so it will be greater than, the sign will change, minus root 2 times xn minus 1, as xn minus 1 is a negative sequence, right? So what we have? This xn minus 1 square is greater than root 2 times minus of xn minus 1. And what is minus of xn minus 1? This is, so this you can, but from here you can see this minus of xn minus 1 is greater than root 2, right? So this is greater than root 2, as minus xn minus 1 is greater than root 2. So what you get? This is greater than 2, or xn minus 1 square is greater than root 2 xn. So xn minus 1 is greater than xn minus 1 square, right? Greater than 2. This, so this one we have got xn minus 1 square is greater than 2. So therefore what we have? Xn minus xn minus 1, this we have 2 minus xn minus 1 square by 2xn minus 1. So now this is same thing as saying that 2 minus xn minus 1 square is less than 0, right? So as numerator is this time also negative and the denominator is also negative, because this time case 2 is the for negative sequence, so we'll get this is greater than 0, as xn minus 1 is a negative sequence. So which is same thing as saying that xn is greater than xn minus 1 for all n greater than 2, which means that xn is bounded monotonically increasing. See here, so we have get xn is a monotonically increasing sequence and which is bounded above, so xn will converge. So therefore xn will converge to some number, let's say L again. So this is saying that, so let me write it, xn is L. Now I can take the limit this time. But now this is a negative sequence, right? So what will happen then? As xn, we have xn minus 1 by 2 plus 1 by xn minus 1. So again take it limit n tends to infinity. This side L, it will become L by 2 plus 1 by L, or L by 2 is 1 by L, or L square equals to 2. So this is a negative sequence, so we will take this to be minus root. So if you start with some negative number, then it will converge to minus root. So therefore limit n tends to infinity xn, this will converge to minus root. So we have completed both the cases. So for the first case, when the sequence x0 is positive, so then the entire sequence become positive, and then the sequence will converge to root 2. Because L is positive, that's why we have taken the positive square root. And now case 2, when the sequence is negative, then the entire, when the initial condition is negative, then the entire sequence becomes negative. So then it will converge to minus root 2. Now let's check which option is correct. First one is saying that the sequence converges to root 2 for all x0 in r minus 0. So option A is not correct, because if we take the x0 to be negative, it will not converge to plus or positive of square root of 2. It will converge to minus of square root 2. So the first one is false. Or the next one, saying that sequence converges to root 2 whenever x0 is greater than square root 2 by 3. So this is true, because x0 is now positive, so the sequence will converge to square root 2. So option B is correct. Check option C. Option C is saying that the sequence will converge to square root 2 whenever x0 belongs to in the interval minus 1 to 1 except 0. But this is again not true, because if we take the negative number, it will not converge to root 2. So option C is not correct. And the option D is saying that the sequence will diverges for any x0 which is non-zero. But you have checked that for x0 positive, the sequence will converge to root 2, and x0, if it is negative, then sequence will converge to minus root 2. So the option D is also not correct. So the only option B is correct. Okay. Yeah, okay. So this finishes this question number 18. Now we'll move to question number 38. Okay. Okay, so let's start. So today we'll solve Gate 2022 question from real analysis. So this is question number 38. What it is saying, that let f be continuous functions on minus pi to pi such that fx is bigger than f0 by 2 for mod x less than delta for some delta in 0 to pi. And let us also define p and delta of x to be the 1 plus cos x minus cos delta whole to the power n for n belongs to natural number. Then 4 options are given. You have to check which one is or are correct. So these are the 4 options. Now, so in order to solving this is the NPTEL reference. Okay, now let's solve the question. So what it is given, f from minus pi to pi to r be continuous function such that fx is bigger than f0 by 2 for mod x is less than delta for delta between 0 to pi. So this is continuous functions in compact intervals, so therefore f is bounded. So therefore f is bounded. So f is bounded means, so mod of fx is less than some quantity c for all x in minus pi to pi. Okay, so we'll use this one, that f is bounded. So what you have to find, you have to find the 4 integral, right? So you have to find this 4 integral. So let us also first analyze what is p and delta. So p and delta of x is given by 1 plus cos x minus cos delta to the power n, where n is natural number. Now let's see what this function is saying. Let me write down. So this is a graph of cos and in minus pi to pi. Let's say this is minus pi, this is pi, this is 0. Let's say this is delta, this is minus delta, right? So this is cos. So at 0 point this is 1. So note that cos is decreasing in this interval. So note cos x is decreasing, cos s is decreasing. on minus on both this side, on minus pi to 0 and 0 to pi also. So we'll use this one, that cos is decreasing. So what will happen? So for 0 to pi, you have to check what is cos x minus delta. Oh, sorry, here I forgot to mention. So this side it will be increasing, means minus pi to 0 it will be increasing, and from 0 to pi it will be decreasing. I will correct it. So for mod x also, when mod x is less than delta, when mod x is less than delta, then what will happen? So let's say positive, but on 0 to pi, means x is bigger than this, less than delta. So as cos is decreasing, so therefore cos x minus cos delta is positive, right? So this is positive because as delta is bigger than, so cos delta will be, so this is decreasing, so cos at the point x is bigger than cos delta on 0 to delta. So so pn delta of x, so this is 1 plus cos x minus delta cos delta. So as this is bigger than 0, so 1 plus this will be strictly bigger than 1 for all n, right? So this quantity will be strictly bigger than 1 for all n. So in this side. So this is, let me say, so this is case 1. And case 2 is 1. So similarly for, so case 2, let me say, when mod x is less than delta on 0 to pi, on minus pi to 0. So means what is this range? So this range is basically minus delta less than x less than equals to 0. So again the same thing happened, right? Because cos is even function. So therefore we have this cos x minus cos delta is again positive, because in this range cos x is bigger than cos minus delta, right? So this is also positive on minus delta to 0. So therefore pn delta of x, so this is 1 plus cos x minus delta cos delta to the power n, which is strictly bigger than n for all n belongs to natural number. Now case 3, when, so let's say when x is lying in this range bigger than delta and less than pi, positive x and which is bigger than delta. So let's delta less than x less than pi, right? So then what will happen? Then cos x minus delta cos x minus cos delta. So there, as x is, cos x is decreasing, so cos delta will be bigger, so this will be strictly less than 0 on delta to x. So what is this then saying? Pn delta of x, so this is 1 plus cos x minus cos delta to the power n. So as this quantity is strictly less than 0, so this is less than 1 for all n belongs to natural number. So this is the case 3, and similarly case 4. What is case 4? Case 4 is when x is lying between minus pi less than x less than minus delta. Then also cos x minus cos delta, which is again in this range. Cos is decreasing, so at the point delta value will be bigger. So this is strictly less than 0 on minus pi to delta minus delta. So Pn delta of x is 1 plus cos x minus cos delta to the power n. So this will be again less than 1 for all n belongs to natural number. So you have get these 4 cases. So using these 4 cases, we will solve this question. So what is the first option? It is saying that limit n tends to infinity, integration 0 to 2 delta fx Pn delta of x dx is 0. So let's check this one. So option A we are checking first. Limit n tends to infinity, integration 0 to 2 delta fx Pn delta of x. You have to find that this limit is 0 or not. So because we know it's, so let's first divide this into 2. So let's write integration 0 to 2 delta will divide it into 2 part. Fx Pn delta of x dx zero to delta fx Pn of delta x dx plus delta to 2 delta fx Pn delta of x dx. So let me call this is to be I1, and this is 1 and this is 2. So you know what is the property of f? We know that fx is bigger than f0 in this region, right? So we'll use this one. So first let's check this one for I1. For I or 1 first do. So this is the integration from 0 to delta. On 0 to delta, fx is bigger than f0 by 2, right? And what we also know that on 0 to delta, so this is the case 1, we know Pn delta, so this is bigger than 1. Okay, and Pn delta is bigger than 1, so this is positive. So therefore, as Pn delta of x, which is bigger than 1 on this region, so you can multiply. So fx Pn delta of x is bigger than f0 by 2 Pn delta of x on 0 to delta. So now integrate both sides. Integrating both sides. From 0 to delta, what will get? 0 to delta fx Pn delta x is bigger than 0 to delta f0 by 2 Pn delta of x. Right, now let's take the limit n tends to infinity. So this is I, right? So this is the, I think, no, I have not defined this. So limit n tends to infinity 0 to delta fx p and delta x dx. So this we have get limit n tends to infinity 0 to delta f0 by 2 p and delta x dx. f0 by 2, this is a simply a constant, so you can take it out. And here you need one Pardew's lemma, that this limit you can take it inside. Okay, so here let me write. So this is simply because f0 by 2 is a constant. Limit n tends to infinity 0 to delta p and delta x dx. Right, now we'll use one lemma. Okay, so here we need one lemma, so let me write the lemma first. So this is called the Pardew's lemma. So what is this lemma saying? So let fn be a sequence of measurable functions. Sequence of measurable functions with fn to be non-negative, means positive measurable functions, if limit n tends to infinity fn x goes to some fx for almost every x. So this is here we do not need, so let me write it in, so I am writing it in general. So then integral of fx, so which is, so what is the meaning of this? So this is limit n tends to infinity fn x, so this is dx is less than lim inf of integral fn x n tends to infinity dx. So it is saying that you can take out the limit from inside, but you have this inequality sign. Okay, so this we will use this. So here we will use this one. So therefore what we have, therefore so this one now also note that in this region what is p and delta, what is limit p and delta. So note that p and delta is positive, so this is the case 1, because p and delta is bigger than 1, so this is positive, so you can apply this Pardew's lemma. And so this is bigger than, this is the f0 by 2 limit n tends to infinity 0 to delta p and delta x. So by Pardew's lemma here, it will be bigger than equals to f0 by 2, so limit will goes inside. Limit p and delta x, right, here we have used by Pardew's lemma. Now what is the limit of p and delta in this region? Note as p and delta x is strictly bigger than 1 for all any natural number, so limit n tends to infinity p and delta so basically it is look like this one, right? 1 plus cos x minus cos delta to the power n, and this quantity is strictly bigger than 1, right? And this quantity is strictly bigger than 1 for all n in natural number. So limit p n delta of x, so it will be infinity, because if to the power something x to the power n where x is bigger than 1, then the limit will goes to infinity, right? So that's why the limit is, so therefore what we have, so using this one, therefore limit n tends to infinity, integration 0 to delta fx p n delta x dx, which is bigger than f0 by 2, limit 0 to delta limit n tends to infinity p n delta x dx, and this side goes to infinity, so this is goes to infinity, right? Because, and this is, so this limit goes to infinity, so therefore this will diverge to infinity, so therefore, which is same as saying that limit n tends to infinity 0 to delta fx p n delta x dx, so this is infinity. So in 0 to delta we have get that this limit is infinity, and what is, so we have checked this first one that this is infinity. What is the now second one? Let's check this one. So this is the easier part. So for 2, what we have to find, this is from delta to 2 delta fx limit n tends to infinity fx p n delta fx x dx, you have to find, right? So now here we will, so that we can, here also we can interchange the limit with equality. So whenever we need to interchange the limit and integral, we need Fubini's theorem, right? So for that we have to check that integrand is absolutely integrable or not. So let's check this one. So claim, so let's first check. So for Fubini, using Fubini's theorem, we have to check that this is absolutely integrable. So let me, so for that we have to check that delta to 2 delta, so this quantity is absolutely integrable or not. So then this is less than, because fx, note that f is continuous, so f is bounded, that we have said earlier. So this is mod of fx times p n delta x dx. So this is c times, and what is p n delta? We know this is basically for delta, for p n delta is from delta to 2 delta, so this is false in this case. Delta to 2 delta, basically which one? This one, right? Case 3. Here it p n delta is less than 1. So use this one. So this is, so then the integral become delta to 2 delta dx. So here we have using these two things, that mod of fx is less than c for all x in minus pi to pi, and p n delta x is strictly less than 1 on delta to 2 delta, right? So this is follows from the case 3. So what is this? So then basically this is saying that c times delta. So this is finite. So the integrand is, so 0 delta to 2 delta fx Pn delta x dx is absolutely integrable. So therefore we can use Fubini's theorem. So by Fubini's theorem, so Fubini says, you're saying that you can interchange the limit and integral if the integrand is absolutely integrable. So by Fubini's theorem, limit n tends to infinity delta to 2 delta fx Pn delta x dx. So you can take the limit inside, limit n tends to infinity fx Pn delta x dx. As f is n independent and the limit of Pn delta, so what is limit of Pn delta in delta to 2 delta? So again, as Pn delta basically the inner function is less than 1, so not Pn delta x, so this is basically 1 plus cos x minus cos delta to the power n, and this one is, we have shown that this is less than 1, right, less than 0 in this region. So therefore limit n tends to infinity Pn delta x, so this is 0, because this is entire, so let me write the entire quantity, it will become less than 1. So if you take n tends to infinity, it will goes to 0. So therefore this one, it is basically delta to 2 delta fx limit Pn delta x dx, and limit of this quantity is 0, so over we will get 0. So therefore what is final, we get limit n tends to infinity 0 to 2 delta fx Pn delta x dx. So we have divided into two parts, right? So this is first part and the second part. So first part we have seen that this one goes to infinity and second one goes to 0. So overall the integral become infinity. So the first option is, it is saying that it goes to 0, so this is not correct. And option B is similar, so let me tell how can you can do this. So this is similar. So option B, it is saying that limit n tends to infinity minus 2 delta to 0 fx Pn delta x dx. And here this is similarly, because what you will do on my, so you will again write it into two part, limit n tends to infinity minus 2 delta to minus delta fx Pn delta x dx plus limit n tends to infinity minus delta to 0 fx Pn delta x dx. And again this part minus 0 minus delta to 0, so again similarly as a, one can show limit n tends to infinity, because p and delta in minus delta to 0, what you will equal again this one, I think the case 2 in minus delta to 0. So p and delta basically the integrand, let me write, then it will be clear for you. This is bigger than 1 and this is bigger than 1. Oh, sorry. Yeah, this is less than 1 and also this is less than 1, because the inner quantity we need to be the less than 1 so that it will goes to 0. So for minus delta to 0, because this is bigger than 1 inside, so as limit n tends to infinity, again this will goes to infinity. So this part minus infinity to 0 part, this will again goes to infinity. Fx p and delta x dx, so this will again be infinity. And what happened to this part? And limit n tends to infinity, minus 2 delta to minus delta fx p and delta x dx. And again in this part minus 2 delta to 2 delta by, you can use for this one I think the case 3 minus case 4 minus 2 delta to minus delta, here it is strictly less than 1, so the limit will goes to 0. So again this one it will goes to 0, so it is 0. So therefore limit, the overall limit again it will be infinity. Limit n tends to infinity, minus 2 delta to 0 fx p and delta x dx is infinity. So option B is again similar. And what happened to option D? Option C? Option C is basically the, again it is similar, minus delta to 0 and 0 to delta you can write. So option C, you have to find limit n tends to infinity, minus delta to delta fx p and delta x dx. So what is this? So this you can write again into two part, limit n tends to infinity, minus delta to 0 fx p and delta x dx plus limit n tends to infinity 0 to delta fx p and delta x. And this one I think in the part B we have shown that this is minus infinity, delta to 0 this is infinity, and from I think part A we have shown in 0 to delta I think, so this is again infinity. So in both, here the both part goes to infinity. So overall using part A and part B, right? So using part A and part B, so this is again goes to infinity. So part C is also done. And what is option D is saying? So option D is saying that limit n tends to infinity, integral from outside the interval minus delta to delta. So there we have to check the limit, right? So let me, so this you can deduce from the earlier. So the option D, so limit n tends to infinity, what is this, minus pi to pi minus delta to delta fx p and delta x dx, right? So again this you can divide into two part, limit n tends to infinity, minus pi to minus delta fx p and delta x dx plus limit n tends to infinity delta to pi, right? Fx p and delta x dx. So minus pi to minus delta I think by A we have done. So this is similarly as this case, minus 2 delta to minus delta case. Similarly, as minus 2 delta to 2 delta fx p and delta x dx, we get, because in this whole range minus pi to minus delta, limit n tends to infinity, fx p and delta x dx. Here p and delta, basically the 1 plus cos x minus cos delta is less than 1, so limit will goes to 0, so therefore we will get this to be 0. And similarly, as I think from delta to 2 delta range, fx p and delta x dx, we get limit n tends to infinity, delta to 2 pi fx p and delta fx dx. This is again 0. These two we can check by similarly, so therefore what we get, so therefore minus pi to pi minus delta to delta, limit n tends to infinity, fx p and delta x dx. So because both the part goes to 0, so overall integral will be 0. So this is, so what we have get, that option A, so option A is not correct, because from we have shown from 0 to delta range it is infinite, so option A is false. Option B again is false, because minus delta to 0, this is again infinite. Option C is again false, because minus delta to delta, this is again goes to infinity. And option D is correct, because here it is outside the interval minus delta to delta, where the p and delta goes to 0. So therefore the whole integral goes to 0 just by Fubini or something, because that we have done. So option D is correct. Okay. Okay, so we have done the question 18 and question 38 for the real analysis. Okay, so let's stop for today. We'll meet again in the next week. Okay, bye.